fractional programming, which is given in the form of fx upon gx, x belongs to s. So this type of function, that means fx 2x upon 1 plus 3x, x upon something, that means this type of programming, this is in the part of the linear fractional programming problem, LFPP, and this is the non-linear fractional programming problem. So NLFPP, because the denominator is in the quadratic form, second order equation. So this is the non-linear fractional programming part. So here S is specified by the finite number of constraints. So constraints should be finite in this case also. And we write the constraint in this form, HIX, which is less than equal to 0. So constraints in this form, HIX, that means I equal to 1 to m, x1x, x2x, x3x, maybe constraints are given, and the function which is defined for Rn tends to R. So real number tends to R. This is known as the ratio function, and we divide into two parts. That means it's a ratio function. That means the denominator is greater than or equal to 0 for every x belongs to x, and when less than or equal to 0. So we write as objective function in this form. We will just multiply by the -1. So ratio function fx upon gx, when gx greater than or equal to 0, we write in this form. If gx less than 0, that we multiply by the -1. You can write a objective function multiply by -1. Just objective function multiply by -1. So here all the functions, that means we use three functions in this problem, such as f, g, and h. H as a constraint, f and g as a ratio function, that means objective function form. So the problem divided into two parts. So linear function, then that means all three are linear function. The functional fractional programming is said to be the linear fractional program. Otherwise, non-linear fractional programming. Non-linear fractional programming. So we define a linear fractional programming problem. So here, for solving the linear fractional programming problem, we define two algorithms. So we shall discuss two algorithms. We give the name as Karn-Cooper, Karnes and Cooper's algorithm, and second is simplex algorithm. First is Karne-Cooper, second is simplex algorithm to solve the following non-linear fractional programming problem. Sorry, linear fractional programming problem. Linear fractional programming problem. So the objective function which is in the form maximum of z equal to CTX plus alpha. T means transpose, alpha upon D transpose into X plus beta. So this is the objective function, and subject to constraints. Subject to constraints in this form: Ax less than equal to b, that means equal to b, and all Asian variables are greater than 0. This is equation number 1. So the value x, c, d, which belongs to real number raised to the power n, tuples of real number, and a belongs to r raised to the power m into n, and b also belongs to r raised to the power m or n and here alpha and beta both belongs to the real number r. Constraints may be in the form of v1, v2, v3, v4, v5, vm, etc. Noted. Manakshi, Mansi, Dipanshi. Okay. So we find out the feasible solution. Feasible solution set S, which is defined as x belongs to r raised to power n, such that ax equal to b and x greater than equal to 0 is assumed non-empty and bounded. That means having some element, that means ax plus b, ax equal to b, that means constraints are given. So as set as having some elements, and then with the elements are also bounded. Set as is also bounded, and denominator gx we write as d transpose t into x plus beta, the denominator which is not equal to 0 for any value of x. So we already discussed here. That means this is the structure of the linear fractional programming problem or non-linear. That means just depend upon the fx, gx or hx. So we define as fx upon gx are ratio functions, so then gx should be greater than equal to 0. So same here we write that means the denominator gx is not equal to 0. That having some functional value such as linear or non-linear. So we are talking about the linear function fractional program problem. So that means obviously this is in the form of the linear function. Linear function which may be in the form of ax plus b type, or maybe in the form of, yeah, you can write general form, that means which may be 2x plus 1, only x minus 3, x minus 5, x plus 5, etc. Because we are considering linear form. So this is the formulation, that means formulation of linear fractional programming problem. So we have given any objective function which is in the form of the fx upon gx, both are in linear form, and also subject to constraint which are in the form of the hx. Hx means hix. Hix means more than one constraints are given in the problem. So we write here in also a general term. You also write in the linear programming problem. That means we make objective function and subject to constraints. Subject to constraints are given in the form a11x1 plus a12x2 plus a13x3 plus and so on a1xn less than or equal to b1. So earlier we also discussed this same thing. That means in the DPP you can solution of LPP with DPP here. So this is this type. That means you can this type of form we write in this form ax plus b. That means we make a matrix a11, a12 of order n by n, and x a column matrix, and also b with the column matrix. We write in the form of ax equal to b. Okay, Dipanshi, Meenakshi. Yeah. So this is the formulation. Now we use the methods to solve the linear fractional programming problem. So we discussed there are two methods here we use to solve the LFPP. That means first is Karn-Cooper algorithm and second is simplex algorithm. So first we discuss about Karn-Cooper. Karn-Cooper algorithm. Karn-Cooper algorithm. So a variable transformation is used to convert problem into a linear programming problem. So same thing follow. That means when we solve a linear fractional programming problem, so first we convert a linear fractional programming into linear programming problem. Convert linear fractional programming problem into linear programming problem. With preserving the geometry of the problem. So let's denominator. First we focus on the denominator, d transpose into x plus beta. We assume that this is 1 upon omega. We assume that this is 1 upon omega. So denominator we write in this form. Now the problem is rewritten as maximum of z equal to C transpose into x plus alpha upon 1 upon omega. So this is the objective function, C transpose into x plus alpha, or we write in place of denominator 1 upon omega. So this can be written as this equal to C transpose into x plus alpha into omega. So this is the objective function maximum of z, and subject to constraint we write as x belongs to s. So x belongs to s, which may be ax less than equal to b in this form. So using the transformation, we use the transformation. Suppose y equal to omega x. When we multiply omega inside this term, so omega x. So the above problem becomes, when we multiply omega into this function, that means we write omega x, so it's just we replace omega x equal to y. So have a problem, that means this problem can be written as maximum of z equal to C transpose into omega x. If we replace omega x as y plus alpha omega. So in this term, and subject to constraints we write in this form, ay minus b omega equal to 0. Now you remember this. So these are the main necessary conditions. That means when we replace ax by omega, so we convert. That means we have a constraint in this form, ax equal to b. So when you put y equal to omega x, that means x equal to y upon omega equal to b. So that means you write as ay equal to b omega. So ay minus b omega equal to 0. So this is our new constraint. Understand? So this is our new constraint. Ay minus b omega equal to 0. And the denominator, which denominator? This denominator. That means this one. D transpose of x plus beta we write as 1 upon omega. Understand? So we use this denominator as a constraint. So how to use this as a constraint? So we write this as in this form. So d transpose x into omega plus beta omega equal to 1. So here we replace x omega by y, and you write as d transpose into y plus beta omega equal to 1. So here we use two variables. which is y and omega. So that means we write as y and omega greater than equal to 0. Greater than equal to 0. So this is our equation number 2. After using the transformation. After using the transformation. Understand? So here this is our main problem. That means this is the main problem. In this problem, we use the transformation. For transformation, we take denominator which is not equal to 0, and taking denominator as 1 upon omega. So denominator equal to 1 upon omega. So just we rewrite the function in this form 1 upon omega. That means we write into omega in this form, and we use the transformation. So for using the transformation, we write this equation as in terms of y or omega. So that means we replace just omega x by the y. So this is our equation number 2. So here we see that the equation number 2, which is in the form of the linear programming problem, which is in the form of the linear programming. That means fractional part is removed. Because in linear program problem, we have some objective function which in the form of the c1x1 plus c2x2 plus c3x3 plus and so on cn xn. So here we have objective function and corresponding subject to constraints. Okay, so this is problem. That means it may noted that the transformed problem that is equation number 2 is a linear programming problem. Linear programming problem with an additional variable. Additional variable we use with an additional variable and one extra constraints. That means we use denominator as a constraint. So additional variable, that means omega, because the problem is given in this form x. So here x is only the variable. X is only the variable, but here we use y and omega. That means omega x replaced by y. So we use y and omega. So that means one variable is additional and constraint one and constraint is also additional. Extra constraints as compared to problem. So the feasible solution of the problem is denoted as S dash. S dash. So this S dash replace into two variable. That means previously S equal to x. Here S replaces y and omega. And the condition we write as ay minus b omega equal to 0. Ay minus b omega equal to 0. And the second condition, d transpose of y plus b omega equal to 1. B omega equal to 1. And conditions, both y and omega, both variables should be positive, greater than 0. So this is the method known as the Karl-Kupper's method to solve the linear programming problem. So just we replace fractional part into linear part. That means denominator consider as 1 upon omega such other function value and or replace into the constraints, the denominator part. So you just do this thing into the Karl Cooper, then solve the problem. When you solve the problems by using the simplex method, So we take one problem. All you noted this? Ankita, Bhavna. Okay. Now we start question. Solve the fractional programming problem. Maximum of z equal to x1 upon x1 plus x2 plus 1. This is our objective function, and subject to constraints are given x1 plus x2 less than equal to 1 and x1 plus 2x2 also less than equal to 1 and x1 x2 both are greater than equal to 0. Both are greater than equal to 0. So this is the linear fractional programming problem due to function having fractional part. This is in the form of fx upon gx. Fx upon gx. So now note down this problem. So we see that the denominator, first we focus on the denominator. Understand? First we focus on the denominator due to this. So that means this one. This is our basic thing. So the ratio function fx upon gx. Well defined, we assume that gx greater than equal to 0. In case gx less than 0, so that means we multiply this objective function y minus 1. So we remember this. So the denominator of this problem is x1 plus x2, x1 plus x2 plus 1. This is greater than equal to 0 or less than equal to 0? This is greater than 0 or less than 0? Which one is correct? Dipanshi? X1 plus x2 which plus 1 which is less than 0 or greater than 0? Not greater than. So this is greater than 0 due to both decision variable are positive. Both decision variable greater than equal to 0. That means when we take the value of, suppose we take x1 0, x2 0, so 0 plus 0 plus 1 which is 1, that means greater than equal to 0. We take value x equal to 1, 1 plus 1 2 plus 1 3 greater than 0. So this gives us greater than 0. So that means our first part. So for ratio function, this means you read this. So ratio function fx well defined, we assume that this is greater than equal to 0. So here we don't assume, we check. Suppose this function given in this form x1 plus x2 minus 5 minus 6 minus 10 minus 100. So some value of x1 and x2 gives a negative value. Or function defined in this form, that means minus x1 minus x2 minus x1 minus x2 plus 1 equal to 0. So we check all these conditions. So both decision variables, that means we write as x1 plus x2 greater x1 plus x2 plus 1 greater than equal to 0 for all decision variable x1 x2. So feasible for the problem. Feasible for the problem. So we apply Carney and Cooper's algorithm, transformation, right method. By using the transformation, we put just that is 1 upon denominator x1 plus x2 plus 1 equal to omega. So you remember this. So here we write this transformation, that means we consider this term d transpose x plus beta equal to 1 upon omega. So just we write 1 upon, we take here 1 upon this term equal to omega, and y1 y1 equal to omega x1 and y1 equal to omega x1. This term you can write in this form. That means x1 plus x2 plus 1 equal to 1 upon L. Both are same thing. So we use this transformation, and because we use two variables, so we replace as y1 as omega x1 and y2 as omega x2. So the problem can be written in this form. So when we replace all things, so that means we write as maximum of z. Maximum of z. What is the value of maximum of z? Because function is given as x1. x1 upon x1 plus x2. x1 plus x2 plus 1. So we write as x1 upon omega. Understand? Our objective function, we write again, you don't confuse, or that means our objective function in this form, x1 plus x2 plus 1, and we replace denominator as omega. We replace denominator as omega, 1 upon something, 1 upon x1 plus x2 plus this equal to omega. Sorry, this is not in denominator, so this is into multiplication into omega. Yeah, we just replace this x1 into omega, or x1 into omega we write as y1. We write as y1. So maximum of z which replace into y1. So maximum of z equal to y1. So this is our objective function. Objective function which means new objective function. And subject to constraints, subject to constraints we write that means first constraints in this form, x1 plus x2 less than equal to 1. So x1 plus x2 less than equal to 1. So we put the value of x1. x1 means x1 plus x2. So we put x1 equal to y1 upon omega. y1 upon omega. So we write as y1 upon omega plus y2 upon omega less than equal to 1. Less than equal to 1. So we write as y1 plus y2 less than equal to omega. Or we write as y1 plus y2 minus omega less than equal to 0. Minus omega less than equal to 0. So this is our first constraint. This is our first constraint. Our second constraint is x1 plus 2x2 less than equal to 1. So x1, in place of x1 we write as y1 upon omega plus 2x2, so y2 upon omega, x1 plus 2x2, y2 upon omega less than equal to is same as 1, less than equal to 1. So this is less than equal to 1. So here we write as y1 plus 2y2 less than equal to omega, and we write as y1 plus 2y2 minus omega less than equal to 0. Minus omega less than equal to 0. So this is the second constraint. And what is the third constraint? We make the third constraint as denominator part. Make the third constraint as denominator part. So this is the first constraint. This is the second constraint. And make the third constraint as denominator. So what is the denominator? We write denominator as x1 plus x2. So denominator, you remember denominator x1 plus x2 plus 1 equal to 0. We write equal to 0. So x1 plus x2 plus 1. Yeah, x1 plus x2 plus 1. So x1 y1 upon omega, y2 upon omega plus 1 equal to 0. And we put this as equal to x1 plus x2 equal to 1. So we put this equal to 1. So we put equal to 1. So you take this equal to 1, denominator equal to 1. And this take equal to 1 as, so we take this equal to 1. So this means we write as y1 plus y2 plus omega equal to 1. So this omega you cannot take here this side. So just you solve for this side. That means first we write equal to 0. Then that means you write equal to 0. So when you write equal to 0 and the final statement you put in this form equal to 1. Equal to 1 because we know that this is our second constraint in the general case. So here we consider as this one. So D transpose of this equal to 1. Remember, D